Welcome back, students. It's Mr. Moss again, and today we're going to look more at your radiation exposure. In this lab today, we're going to look at radiation shielding and what that is and what that does. Now remember, we talked about there's three things: time, distance, and shielding. So in the last lab, we looked at distance. Obviously, the further you are from the source, the less the radiation. It's an inverse squared relationship because of spherical spreading. The time one we didn't really talk about yet, but it's obvious. If you don't spend time near the source, you are not going to get any exposure from the source. So you don't want to be around a source of radiation if you don't have to. Today we're going to look at the shielding part of that equation. Shielding for radiation works pretty much the same way that shielding works when you're talking about arms and armory. So it attempts to block some or all of the radiation from coming to you. So there's different kinds of materials we can use for shielding and different thicknesses, and we're going to explore those things in today's lab. So we're going to go to the radiation shielding lab here, and we're going to begin. Now this is a lot like the lab we used yesterday, except here the distance from the source to the detector is fixed. We can still change what radioactive element we have over here. So there's barium, there's radium, and there's carbon-14. Carbon-14 is a beta emitter. Barium-137 is a gamma emitter. That symbol means gamma. And radium-226 is an alpha emitter. And so that emits alpha particles or helium nuclei. Now you notice that the source to the detector is fixed this time, so this distance between the source and the detector doesn't change. We still have our decade counter in the lower left and our time in the upper right. But this time we have, instead of changing the distance, we can change what the shield material is. Air means basically that we have no shielding, essentially. And you can change the thickness. So the shield thickness can change from thin to thick. So what we're going to do today is we're going to look at how we can change a couple of different things. First part of the lab, we're going to measure the stopping distance for steel. So we're going to select steel as our shield. And we're going to look at all three different types of radiation and see what thickness will stop the counts. So what we want to do is reset, and we want to change the thickness of the steel until we get no counts for 30 seconds. So counting labs are a lot of waiting. Sometimes I did a lot of them teaching nuclear, studying nuclear. And so we're waiting for 30 seconds. My suggestion is you start with the thinnest material because it looks like this material is too thick already. So if I go back to the thinnest material that they have, this is 0.05 millimeters. You can see that when I change the thickness, it restarts the counting. So we want the thinnest material that will stop. So you see I got one count before 30 seconds, so I'm going to go up to the next thickest. And that restarts the counting. Now, when you do it, your thickness is going to be different than my thickness because it kind of randomly determines the thicknesses each time each person opens the lab. So we don't have set thicknesses. All right, so I went 30 seconds at least with no counts. So that means a thickness of 1.3 millimeters will stop alpha of steel, will stop alpha particles. So I can be protected from alpha particles by very thin 1.3 millimeters of steel. Okay, so then what you're going to do is you're going to change the decay type. And you can already see that 1.3 millimeters of steel is not good for beta decay. Now you don't have to wait the full 30 seconds. If you go thicker and you already notice counts happening before 30 seconds, you just go to the next one. So you see I have more counts, so it really is kind of fast. Okay, there I got one count. Oh, there I got two, so I'm just going to keep going. And then you're going to do that for all of them, and then you're going to do it for gamma decay. And what we're trying to do to see is what thickness of steel will stop these different types of radiation. Which is easier to stop, alpha, beta, or gamma? In the second lab, we're going to look at radiation versus the shield material. So what we're going to want to do is have the barium-137, that gamma decay, gamma emitter, and we're going to choose the biggest thickness. So in this case, if we cycle through the thicknesses, you're going to find the thickest is 32.8 millimeters. And so what you're going to do is you're going to measure for just 20 seconds. So I'm going to watch the clock. As long as you're between 19 and 21 seconds, this will work just fine. So what I'm going to do is let it go for 20 seconds. I'm going to try to hit 20 as close as I can. Boo! Yeah, perfect. So as long as you're within 19 to 21 seconds, you'll be fine. So you're just going to record those number of counts for steel. Remember, you want to use the thickest material, thickness that you can, and then you're going to go through the different materials and count for 20 seconds. Now, obviously, the one that has the fewest counts in 20 seconds is the one that's the best for stopping radiation. So we want to look for the fewest counts as the one that's best for stopping radiation. In the third part of the experiment, we're going to look at the thickness of the shielding versus the activity. And so what we're going to do is we're going to keep our gamma detector, our gamma emitter, and what we're going to do is we're going to change the material. We're going to want to use a lead. And then what we're going to do is we're going to change the thickness. So we're going to start with the thinnest amount of lead that we can. And what we're going to do is we're going to time for 100 counts. So you notice over here the counting's going up. And we're going to wait until we get above 100 counts. And it doesn't have to be exactly 100, just above 100. And what you're going to do again is record the counts and the time. And you're going to take the counts divided by the time, and that's going to give you counts per second. So that's going to tell you the rate at which radiation is going through that shield. Now, one of the things we want for this case is when there's no shield, so we're just going to do that when we have air. So what would happen if there's no shielding? That's actually the first one we're going to do. Probably should have told you that first, don't you think? So we got a little time while we're waiting anyway. So, all right, above 100, boom. Okay, so we got 105 counts in 15 seconds. Okay, air thickness doesn't matter because it's just air. There's nothing really stopping the gamma radiation. So then we're going to go back to our lead. And what you're going to do is you're going to change the thickness of the material. You're going to measure the counts and the time. And then you're going to calculate the counts divided by the time. And then what you're going to do is you're going to graph that. So with 0 thickness is going to be the air. And then you're going to increase the thickness of the material. And you're going to go all the way out. Okay? And you're going to measure the different thicknesses of the material and see the effect it has. You're going to count until you get to 100 counts. So the time is actually going to go up as you're counting. Then what you're going to do is graph that and look at the relationship. And so in this case, since we're dealing with radiation, it might be that exponential decay is an appropriate one to use for this. So exponential decay might be appropriate. Just go through all the different ones and try. But definitely 0 thickness is when we just use air. And that's going to be kind of your base count when there's no shielding whatsoever. So that means for today we have 3 quick experiments to do, look at the results. There's some ranking to do, a little bit of graphing to do, but it all should be pretty easy. Just counting takes a little bit of time. See you tomorrow.